Good morning, class. We're back to our class once again. Module 5.1 Structures of Homonuclear Diatomic Molecules. We're going to look at bonding and antibonding orbitals, gered and ungered orbitals. Remember, we mentioned that even and uneven orbitals, energy level diagrams for nitrogen and lighter homonuclear diatomic molecules, energy level diagrams of oxygen, fluorine, and neon and their ions, singlet and triplet states and multiplicity, energy variation for the molecular orbitals, bond order, and we'll conclude. Bonding and antibonding orbitals. Recall that to form a molecular orbital, we linearly combine, that is, add or subtract the atomic orbitals of one atom with the atomic orbital wave function of the other atom. Now, molecular orbitals can be symmetrical or asymmetrical with respect to reflection through the plane containing the molecular axis. Molecular orbitals which are symmetrical with respect to reflection in a plane containing molecular axes are known as sigma molecular orbitals. Those molecular orbitals which are antisymmetrical or asymmetrical with respect to reflection in a plane containing molecular axes are known as pi molecular orbitals. Okay, let's look at bonding and antibonding orbitals again. This is atomic orbital from atom A, atomic orbital from atom B. Look at their energy is at this level. This energy is increasing this way. Look at the energy is here. Now, when this atomic orbital combines with this atomic orbital through linear combination of atomic orbitals, we are going to get two molecular orbitals. One is this phi A plus phi B, and that's what we have here. It will give us a sigma bond, and that is bonding orbital, lower energy than that of atomic orbitals. Look at the energy here. If you extrapolate this line, you meet the energy here, whereas the energy of this atomic orbital is here, which is higher than the energy of this. That's why it's down here. Now, the other linear combination is phi A minus phi B, which gives us anti-bonding orbital. Look at the energy here going towards this way. Now, because there is one electron here, there's one electron here, and there's one electron here, we have only two electrons. The two electrons have entered the bonding orbital. There's no electron in the anti-bonding orbital. This same energy level we have shown here for hydrogen, particularly one hydrogen has one electron, another hydrogen has one electron, forming this. Assuming it is helium here and helium here, then we'll have a total of 4 electrons. So 2 electrons will enter here and 2 electrons will enter here. So this same thing we've seen here is the same thing we have here showing in terms of overlap. These are the atomic orbitals, this and this. So we have subtract and we have add. Add gives us bonding, which is sigma. Subtract gives us anti-bonding. Remember, that's the same thing that we have here. Subtraction, we have addition here. This is the energy level diagram, and this is the formation of the orbital. That is the linear combination of the atomic orbital, the way the orbital is formed. The same thing happened when we look at 2p. Remember that the p orbital has px, py, and pz orbitals. So look at here. This is linear. Pz to pz gives us antibonding and bonding. This is sigma 2p, whereas this is sigma star 2p. This is antibonding. Look at the nodal plane here. Now px to px here will be side to side. As long as this pz has overlapped end to end, the other two will overlap side to side. Assuming it is px that we use here, then here will be py and pz. That's exactly what we're saying. So this is what is going to happen for px side to side, py side to side. Then PZ has overlap end to end here to give us sigma sigma. All this side to side will become pi bonds. That's why you're seeing pi 2p, pi star 2p, pi 2p, pi star 2p. This pi here and this pi here are of the same energy. We'll see that. This pi star here and this pi star here are also of the same energy. So the same overlap that has happened with s orbital, this is the overlap for p orbital. The 3p orbitals we have px, py, and pz orbital. Now, if lambda is the quantum number related to the component of the electronic orbital angular momentum along the molecular axis, then sigma orbitals have lambda equal to 0, and pi orbitals have lambda equal to 1. We must note this. We must note this. It's very, very important in the spectroscopic term symbols we are going to calculate. Sigma orbitals have lambda 0, while pi orbitals have lambda equal to 1. There is a center of symmetry. If we perform an operation of inversion, the sign remains unchanged. It is therefore called even. Remember, we met this before, or symmetrical or zeroed, denoted by G. When we perform an operation of inversion and the sign remains unchanged, then we have a center of symmetry. Okay, then denoted by G, the molecular orbital is asymmetric with respect to inversion through the center. And we denote that as U and say it's uneven. That's why we'll say gered and ungered orbital. When we have symmetrical, it's G. When we have asymmetrical or uneven, it is U, that's ungered. Hence, for sigma orbitals, sigma star is U and sigma is G. For pi orbitals, pi star is G while pi is U. So this is very important because we're going to apply this in our calculation of spectroscopic term symbols. Energy level diagram of nitrogen and lighter homonuclear diatomics. Now we have energy level diagram. These energy level diagrams are divided into two. For lighter homonuclear diatomics, for example, of course, for hydrogen, helium, lithium, up to carbon, there won't be any difference. They are the same, both lighter and heavier. But when it gets to up to nitrogen, so we take this as the energy level diagram for nitrogen down. That is atomic number 1 to atomic number 7. And when we get to atomic number 8, the diagram will change. You will see that. Look at it. Of course, we have looked at the 1s. So we're not including 1s here. But the same thing that is happening with 2s here, we have a replica of this diagram down here, which shows us for 1s. This is 2s combining to give us sigma 2s and sigma star 2s. So we have 1s combining to give us sigma 1s and sigma star 1s. Then when it comes to 2p orbital, remember we have 2px, 2py, and 2bz as we see in the last slide. 2p here, 2p here. So you now see the pi is of the same energy like I told you is here. Then sigma 2p is here. Then sigma star, the two of them is of the same energy here. And then this one energy is highest. So when we look at the molecular orbitals, we'll see that we first get sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then we'll have these two, pi 2p, two of them of the same energy. We'll have sigma 2p, then we'll have pi star, then we'll have sigma star. That is the energy level for nitrogen and the other lighter diatomic molecules. And there are ions also, if we're talking about N2 plus or N2 minus, and so on. Now, using that energy level diagram, for hydrogen molecule has 2 electrons. Look at the configuration, H2 equal to sigma G1s. Remember we said sigma is even, that is Jared. Now the ion H2 plus, one electron is lost, so we have sigma G1s1. For helium molecule, 4 electrons, we have sigma G1s2, sigma star U1s2. For the ion, 1 electron is lost. This is the same. Then here, 1 electron is lost. Now for nitrogen, 14 electrons, we have sigma 1 G1s2, sigma star U1s2, sigma G2s2, sigma star U2s2. Now we'll get to the pi. The 2 pi's are of equal energy before we now get to sigma 2p. If you count the electrons here, 2, 4, 6, 8, 10, 12, 14. That's 14 electrons. So if you're talking about N2 plus, 1 electron will be lost. If you're talking about N2 minus, it will gain 1 electron, and the next energy level will be here. Now we are looking at the energy levels for oxygen, fluorine, and neon and their ions. You see what's going on? Now it has changed. The same 2s, the same thing is here. If you look at here now, instead of having these 2 pi down here, the sigma is now the one down. So the 2 pi is in between, the pi star is in between, and sigma is also out. So there's a change here. It's practically the same, except that there's an interchange between this pi here. Instead of coming first, the sigma 2p is coming first. And we use that energy level diagram to do the electronic configuration. 18 electrons for fluorine. It enters that way. Look at the 2 pi. The sigma comes first. This 2 pi comes. Then this 2 pi star also comes. What is now left is the remaining sigma star. For oxygen, 16 electrons. We enter that. This gives us something very important. This and this are the same energy, degenerate orbitals. So that's why you see 1 electron, the same Hund's rule in atomic orbitals. The singlet and triplet, we use oxygen. Now net bonding orbitals, if we check the net bonding orbitals in oxygen, we have these orbitals which can hold 4 electrons are filled. If the 2 electrons occupy one of the orbitals, that is the ground state, S is equal to 0, that's the spin. And we say that is in the singlet state. Because remember, our multiplicity is 2s plus 1. So if it is 2s, 2 times 0 is 0 plus 1 will give us equal to 1. And we say it's singlet state. However, because of electrostatic repulsion between the electrons, the most stable state will be that in which electrons are assigned as this. That's what we did in the electronic configuration of oxygen. This is what we saw, 1, 1. The total spin of oxygen is therefore S will be equal to 1. And its multiplicity, if you put 1 here, 2 times 1 is 2 plus 1 will give us 3. And we therefore say that oxygen is in the triplet state. This is the more stable state configuration. The ground state of oxygen is represented by sigma to power 3. This 3 is the triplet state. So we're going to see that in the spectroscopic term symbol. And because of this, we say that oxygen is paramagnetic. Now the energy variation, that is how these energies are filled, is what we have done here. For the first one, which has these energies for nitrogen and the lighter orbitals, G1s is less in energy, these and these are equal, these and these are equal, and then this. Now for oxygen, look at it, this, the same here. You see where this pi comes in, it is no longer pi first. Sigma is coming in before you have the 2 pi here, then have the pi star before the sigma. That's the difference. Bond order can be defined as the net bonding in a diatomic molecule denoted by B, and it's given by half n minus n star, where this n is number of electrons in bonding, and n star is the number of electrons in antibonding orbital. Thus, each electron pair in bonding orbital increases the bond order by 1, and each pair in antibonding orbital decreases it by 1. For hydrogen, bond order is 1, but for helium, bond order is 0. Therefore, there is no bonding. And of course, that is why you don't have helium existing as He2. There's nothing like helium molecule ion. Helium exists as a monoatomic gas because there's no bonding between helium and helium. The greater the value of the bond order, the shorter and stronger the bond strength. We can also define bond order as bond order equal to number of electrons contributing effectively to bonding divided by 2. Therefore, single bond order is 1, number of electrons 2. Double bond order is 2, number of electrons 4. Triple bond order is 3, number of electrons is 6. Look at an illustration. We are saying that show if N2 will have a larger dissociation energy than N2 plus will have a larger dissociation energy than N2. We'll solve that. N2, look at the bond order is 3. N2 plus, the bond order is 2.5. Since the cation has smaller bond order, we expect it to have smaller dissociation energy. And we have looked at this experimentally to confirm what we got. Thank you very much. We looked at bonding and antibonding orbitals, gered and ungered orbitals, energy level diagrams, singlet and triplet states, energy variations for these orbitals, and I hope you enjoyed this class. See you in the next class. Thank you.